Well, hello, Math One, Honors Math One. This is Mr. Roberts from Shasta High, and I'm going to be going over the Chapter 5 test. This was a brief test, not a lot of time in the day, just a single piece of paper, front and back. Let's start with the first question. The first question says the first three terms of a sequence are, and then it gives us those values. Now, the thing about a sequence is there's two kinds we've discussed, arithmetic and geometric, and it is a arithmetic sequence if these terms have a common difference. That means that we're adding the same value, either positive or negative, repeatedly to get to new terms. And I said common difference because the difference has to be the same. So if I was to grab my calculator and just, for example, take that middle term, 480, nope, I'm going to take the last term, 162, and subtract the previous term, 486, I can see I get a difference of 324 that's negative, right? It decreased by 324 when it went from the second to the third term. But this is not arithmetic if that's not a common difference. Meaning, if I take the 1458, and I subtract from it 324, I have to get the same value, the middle term, right? And I don't. I get 1134. So this sequence, any two terms have a difference. What we need is a common difference. We don't have a common difference here. So this cannot be arithmetic. So the other option that we've looked at this chapter is, well, is it geometric? Does it have a common ratio? And to calculate a common ratio, to see if there's a common ratio, let's just find we'll find the ratio between two terms. So I'll take this last term, 162, and I'll divide it by the previous term, which is 486. And you can see I get this, right, which is, if I kick it into a decimal, it's 1/3. So the question is, every single time I jump forward, am I multiplying by the number 1/3? And if I was, then it would be geometric. So to verify that, I'm going to take the first term, 1458, and I'm going to multiply it by 1/3. And when I do that, you can see I get the middle term. And that's great because I know if I take the 1458 and I multiply it by 1/3, I'm going to get the last term. So I can see that this is a geometric sequence, and I'm going to generate the terms by multiplying by the number 1/3. So the first thing I'm asked to do is complete this table. So, okay, let's complete it. The first term was 1458. The second term is 486. And that third term was 162. So on my calculator, just to verify, I'm going to go ahead and grab the 1458. I'm going to press enter to put it on the stack, and I'm going to multiply by 1/3. So here's the 1/3. I multiply by 1/3 once, I get 486. I multiply it by again, I get 162. I multiply it by again, I get the number 54. There's my fourth term. And I multiply it again, and I get the fifth term of 18. So you can see I've extended this table. It's clearly geometric and has a common ratio. And we're just moving forward by multiplying by 1/3 each time. Next, what is the generator for this sequence? And there's a reminder, a generator contains both an operation and a value. For this sequence, the generator is multiply by the number 1/3. And it's really cleaner just to think about it in terms of what we're multiplying by. Some of you wrote divide by 3, and that's fine. I accepted that answer. The next thing it says, what is the zero term of the sequence? So you can see we were told the first term, but the question is, well, what's the term that came before that? What's the term back here? Well, in order to get the zero term of a sequence, what I'm going to do is take that first term and do the opposite. Instead of multiplying by 1/3, I can divide by 1/3, or I can multiply by 3. So let's take that first number in the sequence, which was 1458, and I'll just go ahead and divide it by 1/3. Right? Dividing by 1/3 is the same as multiplying by 3. You see that I get the number 4,374. So I've now got the zero term, right? And I've got the common ratio of 1/3. And I know I just did this, but I want to run this again. So I've got that number on the stack. I'm going to times it by 1/3. And I can say my zero term becomes my first term, second, third, fourth, fifth. Easy. All right, last, or no, two more. Next, it says find the explicit rule for this sequence. Okay, it is geometric, which means I'm repeatedly multiplying by the same thing again. and it starts at a particular zero term. So to get to any term on the sequence, right, to jump to any term on the sequence, t of n, is going to equal that zero term, right, where you're at before anything happens, which is 4374, times a bunch of 1/3. How many 1/3? Well, it depends on what n is, right? If n is the number 1, I would be multiplying by a single 1/3, and I would get this first number in the sequence. If n was 2, I'd be starting with the zero term, and I'd be multiplying by n twice. I'd be multiplying by 1/3 twice, and I get the second term. So this term number, right? These are the n's, and when I plug that in, it gives me the value of the sequence at that point, t of n. All right, last question. It says write the recursive rule for this sequence. So the recursive rule requires two things. It requires knowing where to begin and how to move forward. So for this sequence, where to begin? Well, the first term of the sequence was the number, I just forgot it. It's 1458. So 1458. So that's the beginning part. And now the recursive rule. The recursive rule says, hey, if you want to get to the next term in the sequence, if you want to get the value of the next term in the sequence, right? This is the value of the first term of the sequence, but the value of the next term of the sequence is the value of the current term, right? The value of the current term times the number 1/3. And I might write this like this. I think I like how this looks better. It's just 1/3 of the term that you're currently at, but I would accept either one of those. So again, this t of n represents the value at a particular spot n, and then t of n plus 1 represents the next one in the sequence. So this just reads the next term in the sequence is 1/3 of the term that you're at. That's the recursive rule. And these two together, right, form the recursive rule. Next, the rebound ratio of a moon ball is 0.83. I own several of these. I've checked it. It might be a little bit lower, maybe 0.82, but it's pretty good. It's very close to a golf ball. The moon ball is dropped from a height of 450 inches, and then it says calculate the rebound height of the ball after one bounce. So remember in class, that rebound ratio is that common ratio. Every single time this ball bounces, it recovers 83% of its previous height. That means that 17% is going away, right? 17% of the height is going, we're losing it, but 83% remains. So what's the rebound ratio, or what's the height that returns to after one bounce? So here's no bounces have happened yet, 450, and I'm just going to multiply that by that common ratio, the rebound ratio, and it tells me, well, after one bounce, this ball would be sitting at 373.5. That would be the height it would return to, and then it would begin falling again because of gravity. The next one says find the rebound height after a second bounce. So I'm just going to press enter on my calculator again, and after a second bounce, I'm going to round that to 310. And these were expressed in inches, so I should probably put units here, inches and inches. So there it is after one bounce, after two bounces. Next, find an explicit equation that could be used to find the height of the ball given the number of times it bounces. So the number of times it bounces, I would say, is n, right? This is where it's at 0 bounces. This is at one bounce, n is one bounce. And over here, n was 2 bounces. So this explicit rule would look like this. The height of the ball after n bounces is the the zeroth term, right? No bounces have occurred, times 0.83 raised to the power of n. So each time it bounces, it maintains 83% of its previous height. It's losing 17%. And then the last question is find the rebound height after the sixth bounce. A lot of options for doing this. I can just go ahead and take the number, the 450, enter, and I could say times 0.83 and then count. This is one bounce, two bounce, 3, 4, 5, 6 bounce. I'm going to write this down and then I'm going to verify it a different way. So after 6 bounces is about 147 inches. Another way I could do that is I could open up and you create the table, right? I could write the function for this, which is 450 times 0.83 raised to the power of, and I'm using x here because I'm on the calculator. When I do this now, I'll start at 0 and I'll let it go. So notice that it says the 0 term is 450, no bounces have occurred, and I can just go down to 6 bounces, and you can see there's my 147. So after 6 bounces, we expect this ball to return to a height of 147 and then begin falling again because of gravity. All right, let's move on to the next question. Next question says simplify each expression, and there's 3 of them here. Let's take a look at this first one. This first one has just 2 different things that are being multiplied, right? The number 5 is being multiplied. Oh, 3 things. There's 5 that's being multiplied. There's some x's and there's some y's. Remember, negative exponents indicate that we're dividing that by that thing. So when I see that I'm multiplying what's happening here, right here, if I look at this part of it, what's happening is I've got some number, I'm dividing by x 3 times, and then I'm multiplying by x 7 times. One way I could look at that is I can write that down. That's x to the 7th, right? 7 factors of x over x to the 3rd, right? That's me dividing by x 3 times. And when I do that, that's equivalent to me just multiplying by x 4 times. So I don't have to divide by x 3 times and then multiply by x 7 times. I can just multiply by x 4 times. So the first thing I'm going to write down is I do have a factor of 5. And then this is me just multiplying by x 4 times. And then I've got this y to the negative 3rd. Now, that is me dividing by y 3 times. And I could just put that down in my denominator and be done. I do want to look at this as an opportunity to reiterate this justification for why I can just move that into the denominator. One thing I could do is I know that I can always take something and multiply it by the number 1. So I don't care what I put here, right? If I put happiness over happiness, that's the number 1, and that just reduces to the number 1. So as long as I put the same thing in the numerator and denominator, it's a 1. What I want to do though is I want to go ahead and I'm going to multiply the numerator and denominator by y to the 3rd power and y to the 3rd power. And when I look at this, what's going on here is this is me taking something and dividing by y 3 times and then multiplying by y 3 times. So that's equal to 1. So I can see if I want to eliminate, especially a complex negative exponent, if I just multiply it by the same thing, but instead of being to the negative 3rd, I go to the positive 3rd, I'm just undoing that. So this just becomes the number 1. And if you look at it, this is now the number 1. And I'm allowed to do this because I'm multiplying by the number 1. Where are my factors of y now? They're in the denominator, right? I'm just dividing by y 3 times. So the simplest way to write this expression is 5x to the 4th power divided by y to the 3rd power. Again, this is true, right, for the reasons that we said, but as evidence of its truth, you could pick any random value of x and y and verify that the original expression and this expression will always produce the exact same outputs, regardless of the value of y or x that you pick for them. Although 0 may be problematic because division by 0 is not fun. Let's go to part B. In my numerator, you can see I'm multiplying 5x cubed, right? 5 times x cubed is there, but then that thing gets squared. And when I square 5x cubed, that's equivalent to me multiplying it by itself. So I can write 5x cubed times another 5x cubed. So now you can see that I'm multiplying by a 5 times a 5, which is 25. And then I have 3 factors of x times 3 more factors of x, which means that's x to the 6th power. So that numerator is the same as 25x to the 6th. And then in my denominator, I have this x to the negative 5th. Okay, well, we've just talked about how I can eliminate this negative exponent, right? I'm going to multiply both I don't need a keyboard. I'm going to multiply both the numerator and denominator by x to the positive 5th. That will get rid of the negative exponent below and give me just a positive exponent. So the big thinking here is this is equal to 1, right? That's 1. Therefore, my denominator is now just 1. But if you look at what I've got in my numerator now, there are now 11 factors of x. So this is 25 times x to the 11th power. Again, this original expression and this new expression, right? And this is me rewriting it. So these two things should be equivalent to each other. If I pick any value of x and I look at the numerator, the first original expression that I'll box, and I compare that to this simplified version, right? They should always produce exactly the same outputs. And if you test that and something's not right, then you need to think about, okay, well, what was my logic to get to here? Because maybe I'm missing something, or maybe I don't understand something. So it's really, really powerful when you can get to a point where you reflect on what you've written down and then think about the correctness of it. Let's go to the last one in this question. It's part C. In part C, look, that numerator, I only have factors of A and factors of B. Those are the only things that are being multiplied by. In the numerator, there are 10 factors of A. So I can start by writing, hey, this is A to the 10th power. And then I've got 5 factors of B up there. And in my denominator, I have B to the negative 4th. How do I get rid of that? I'm going to multiply by B to the positive 4th in both the top and bottom. And that is going to give me, in the numerator now, I have 9 factors of B. So this is A to the 10th times B to the 9th power. That's a 9. And again, these just equal the number 1 because this is in the denominator. I'm like dividing by B 4 times, and then I'm multiplying by B 4 times. So that's just going to equal the number 1. And in my numerator, oh, why can I do this? I can do this because that's the number 1, right? All right. That is our final answer for part C. Let's move on to the second page. Yeah, that's the second page. Now, it got cut off here, but the directions for the second page say solve, right? And the art of solving an equation is not just getting to what x is, but also communicating with the reader of your solution what you're doing and how you do it. So it's really important to think about, how can I neatly write down these steps so that others can follow in my tracks and understand what I'm talking about? So let's go ahead and start with this one. This is going to collapse to this idea of looking inside. I don't need it. I don't need the touch keyboard to go away. Looking inside, because I've got this square root thing. But before I can look inside and contemplate what that square root is, it's really convenient to isolate it first. So I might look at this as like, hey, this is 47 plus 3 times some number, right? I don't know what this is, but it's some number. And then it's supposed to equal 74. So what I'm going to do is I'm going to get that blue box alone first, and then it will help me more clearly think about what has to be inside of it. So to get it alone, I'm going to subtract 47 from both sides. So, and I'm not ashamed to do this because you've seen me make arithmetic mistakes, although I don't really need to do this. So if I take the 74 and I subtract 47, I get the number 27. So I can rewrite this as 3. I don't want a blue pen. I can write this as 3 times the square root of 2x minus 9, and that equals the number 27. What I'm going to do now next is I'm going to divide both sides by 3. Over on the left-hand side, that's going to become the square root of 2x minus 9, and that will equal 27 divided by 3, which is, of course, the number 9. So it's going to equal the number 9. At this point, I'm just thinking a bit here. Oh, I've got the square root of something. The square root of something is 9. What's that thing? The square root of something is 9. What's that thing? I'm not going to go into the fractional exponents. Let's just say, looking inside, this value inside of this has to be the number 81, because the square root of 81 is the number 9. So what my goal is I need to turn this thing into the number 81, right? That has to be the number 81. And if you're not good about like square roots and squaring, just square the 9 and you can see what that thing inside has to be. It has to be 81. Well, how do I make it 81? It's easy. It's algebra. I'm just going to set 2x minus 9 equal to 81, and that will turn it into 81. So on the left-hand side, or right-hand side rather, there's a number 81. I'm going to add to that 9, and I get 90. Okay, so 2x is 90. And if I divide both sides by 2, I get that x is 45. Divide by 2, you can see it's the 45. Now, I always like to check my work, right? I think that this is a nice logical step-by-step solution, but I do want to take a moment and check it. And I'm going to go all the way here and store that value as x. So I just told my calculator, hey, I want you to believe that x is 45. So if I ask my calculator what x is, it says, okay, you told me it's 45. So it's going to believe that. Now it's easy to check this. I could just take 47 plus 3 times the square root of, I have to hit the second key to get square root of 2x minus the number 9. And notice when I press enter, I get 74. So when x is 45, right, both sides of that equation become 74. 45 is the value that's the solution to this equation. All right, let's go to our second equation. Second equation, a great strategy for this would be to do a rewrite. If I look at this part on the left-hand side, it's kind of a mess. It's a binomial times a binomial. So I'm going to rewrite that thing. If I rewrite this without a generic area model, I get 3x squared minus 3x plus 2x minus 1, which I can simplify as 3x squared minus x minus 1. So that's just what's inside of that orange rectangle. Now, yeah, for sure, if you want to, you can do a 2x2 generic area model. So it would look something like this. And I'll cut it into 2 regions this way and 2 regions this way. And you can see I'm multiplying 3x plus 2 times an x minus 1. So in order to multiply that binomial, there's 4 things that have to happen, 4 multiplication problems. The first one is, what is x times 3x? Answer, 3x squared. Again, I'm multiplying to get these areas. Right below that, I've got negative 1 times 3x, which is negative 3x. Upper right box, I've got x times 2, which is 2x. And below that, I've got negative 1 times 2. And you can see I made a mistake. This is supposed to be negative 2. You know what? I'm really happy that I wrote down that generic area model because it helped me catch this. So this is going to be minus 2, minus 2. And I would have caught that eventually when I realized, hey, my answer's not working, but it's nice to get that now. Oh, how arrogant. You can see why I check things, right? I make mistakes. Now, I need to copy down something else, right? I've forgotten these parts, so I'm going to write that below that. So I'm going to say plus 7x plus 4. And then over on the right-hand side, we've got 3x squared plus 47. So I'm going to do 2 things at once. I don't like to do that, but I can see that these are both positive, 3x squared, and I've got 1 on each side. So if I subtract that positive 3x squared from each side, it's gone. The next thing I'm going to do is I'm going to simplify the left-hand side a bit. Right? There's a negative x that I'm going to combine with 7x. And there's also a negative 2 that I'm going to combine with the positive 4. So on the left-hand side, if I simplify this correctly, that's the same as 6x minus the number 2. And over on the right-hand side, I've just got 47. Oh, this is, we're almost done. Let's add 2 to both sides. We get that 6x is 48. And then finally, x is going to be 48 over the number 6, which does reduce. In fact, let me 48 over 6. Both of them can be divided by 2. Wait a minute. What? 48 over 6. 48 over 6 is 8. 7. Oh my gosh. Look at this. This is why I've got to think about these things. I was intending to add 2 to both sides, right? Add 2 to both sides. And I failed because I clearly added 2 to the left-hand side, but I did not add 2 to the right-hand side. This is supposed to be the number 49, 47, 48, 49. And therefore, this is also supposed to be the number 49. So I'm so glad that I caught that. So let's go ahead and look at this now. So I'm looking at the number 49 over 6. Does that reduce? It doesn't reduce. All right, so I, I'm so suspicious of this answer now. I'm going to go ahead and check it. So I'm going to take that number 49 over 6 and I'm going to store that as x. Watch me not have the right answer. Let's confirm that this works or doesn't work. So I'll write the original left-hand side, which was open paren, 3x plus 2, close open paren, and I've got x minus 1, close it, plus 7x, okay, and then 7x, not 74, plus 7x, and then plus 4 more. I get that this becomes the number 3013 over 12. Let's look at the other side. 3x squared plus 47. That gives me a different number. There's a mistake here. There's no two ways about it, right? So I got to hunt this down. So let's start. 3x squared, that's clearly minus 3x plus 2x minus 2 we fixed. And then, yeah. And then there's a plus 7x and a plus 4. 7x, oh, I can see it. It's right here. Here's my mistake. I combined negative 2 with positive 4, and I wrote down negative 2. Except it's not negative 2, it is positive 2. So there's a lot of cascading things that happen after that point. So I'm going to leave those circled in red because I need to think about that, man. I need to think about slowing down. Let's see, 6x is equal to, so I'm now adding, no, I'm not going to add. This is going to become positive 2. So I've just fixed that mistake. Okay, so I've got 6x plus 2 is 47. I need to subtract 2 from both sides. So from both sides of this, I'm going to take away 2. I get 45. All right. Now I've got x is 45 over the number 6. Okay. 45 over 45 over the number 6. Looks like that does reduce to 15 over 2. So this is what I think my answer is. I'm going to store that as x, enter. The thing I love about this calculator is I don't have to type the sides again. I can go up and grab the left-hand side that I typed already, reevaluate it, and it gives me 863 over 4. I'm going to go grab the right-hand side of the equation, which is here, and now I'll reevaluate that with my new value of x, and I get 863 over 4. So this is clearly the value of x that makes both sides of this true. And that was really a long, hot, fought for answer, right? That's an example of being persistent and catching mistakes, and then at the end asking yourself, does your answer do what it's supposed to do? And yeah, it does what it's supposed to do. All right. That was a little bit planned. I'm not going to make any more mistakes for the rest of this video because that's taxing to watch people make mistakes and you want to scream at your TV. So the next thing is an example of this technique we've called fraction busters. So I'm going to go ahead and remove all of the fractions in one step by multiplying by things that will have contain factors of 3x, right? I have to have a 3x, I have to have a 2, and I have to have a factor of x. Well, it turns out the thing that will take care of all those at once is just 6 times x. 6 contains 3 and it contains 2, and 6x contains a factor of x. So my goal is to multiply each one of these numerators by the number 6x. And don't forget that there is this negative here. All right, so let's do that. I'm going to write it out. So I'm going to write 6 times x times 2 divided by 3x plus 6 times x times 1 divided by 2. On the other side, that's going to equal 6 times x times 45 over x, and then minus 6 times x times the number 10. Okay, so now let's recognize that there's some ones here that we can get rid of. This was a nice clean number 1, right? X over X is gone. The next thing I see is, well, this is an X divided by X. That's going to be gone. And then I can do the 6 divided by 3. 6 divided by 3 is the number 2. So this first part is going to become 2 times 2, which is the number 4. And then after that, I'm going to have the number, let's see, 6 divided by 2 is 3. And 3 times x is going to be, this is going to become plus 3x. Over on the other side, I'm going to have 6 times 45, which is the number 270. And I'm going to subtract from that 60x. All right. So it was a step or two, but you can see by multiplying by 6x, I eliminated all the fractions. And now I'm just looking at this. I'm going to add 60 x's to both sides. So that's going to give me, this is 4 plus 63x is equal to 270. Now I'm going to take my 270 and subtract 4 from both sides. When I do that, I get 266. So 63x is 266. And then finally, to get my answer for x, I'm just going to divide both sides by 63. That's fun. That's going to be a crazy looking fraction. Maybe it reduces. Let's see. Well, I'll just write it down first here. So it's going to be 266 divided by 63, which maybe it reduces, maybe it doesn't. I'll take 266 and I'll divide that by the number 63. And I get, oh, it does reduce. That becomes 38/9. All right, so here is an answer. Now, I told you I wasn't going to make any more mistakes, but that doesn't mean I shouldn't check my work. So store this as x, and let's verify the left and the right-hand side are the same. The left-hand side was 2 over 3x. And then to that, we're going to add 1/2. And then to that, we're going to, oh, that's all that's on that side. So that equals 25/38. Let's look at the right-hand side. The right-hand side has 45 over our value of x, and then we are going to subtract the number 10 from that, minus 10. And when I do that, I get also 25/38. So this is a clearly correct answer because it made both sides of that equation 25/38. Last question in this group is D. And I think this one's given us a bit of a break. This looks like it's the easiest of the 4. I'm going to distribute this -2 to both of these terms, right? There's 2 terms inside the parentheses. When I distribute it, I get a -6x. And when I distribute that -2 to the -7, I get plus the number 14. And then I have plus 4x minus 9 is the same as 2x plus 11. I have some like terms I can collect on the left. I made a mistake with this recently. When I combine those, I'm going to get -2x, -6x plus 4x. And on the other side, I have 14 minus 9. Robert, you did not just type that on your calculator. I did, but you can see, I think subconscious, I was typing the answer, right? 14 minus 9 is the number 5. So this combines to give me a, it's just a positive 5 plus the number 5. And I'm writing down 4. I say the word 5, I'm writing down 4. Slow down. On the other side, I have 2x and then plus 11. Now, part of me is tempted right here because I see what looks like 2x on both sides, except this is a -2x, right? So when I look at this, what I'm going to do is not think of this as positive 2x and combine them and we get a equation with no solutions. I'm going to add 2x to both sides. When I do that, this side becomes 5, and the other side becomes 4x plus 11. Now, if I take the number 11 and subtract that from both sides, 5 minus 11 is -6. And on the other side, when I subtract 11, I just get 4x. So therefore, -6 over 4 is what x is, and that reduces to negative 3 over 2. So x is negative 3 halves. I'm going to leave this here. If I'm wrong, cue this video up and show me in class and say, Roberts, the one you didn't check is the one you missed, right? So check it, make sure I'm correct. All right, let's move on. Next question says that we are going to find the output generated by the given input, or find the input that produces the given output. So you can see on one of them, I'm giving you what the input is and asking you to find the output. Over here, I'm telling you what the output is, and I'm asking you to identify the value of x that would make that true. So they're kind of reverse values of each other. I can't tell you the number of times I see this mistake made, so please be careful. When you're squaring a value, use parentheses, right? Especially if you're going to type it into your calculator. I am squaring negative 2. When I square negative 2, I get the number positive 4. So that's an important distinction there. So I've got negative 2. I'm going to be squaring this. And then on the other side, what do I have? Well, let's continue. Then I'm going to say now plus 4 times also negative 2, and then I'm going to add 10. So if I look at this, right, when I square the negative 2, that's going to become a positive 4. And then 4 times negative 2 is going to become a minus 8. And then I'm going to add 10 to that. And I can use the associative property and do either one of those first. I'll just go 4 minus 8, which is negative 4 plus 10. And when I combine those, I get the number 6. So this is 6. If you got an answer of, what was it? I saw a lot, negative 2. What's the problem is more than likely is you're not correctly squaring the number negative 2. And I've talked about this. It's the calculator is just completely correct, right, in how it deals with this, but we're not correct on how we understand our calculator's behavior. If I type this and then this, what I'm saying here is I want to know what the opposite of 2 squared is. So if you look at this, there's this negative in the 2. I'm not squaring negative 2. This is the opposite of what 2 squared is. That's why when I press enter, I get negative 4. But I'm being asked to square x, and x is negative 2. So this is the correct way of showing there's the negative 2, square that, and when I square the negative 2, I get positive 4. All right, the next question is, I know what the output is, but I'm asked to find the input. The best way to attack this is just to write the definition of the function, which is 1/3 of x plus 51. And I want to know the value of x that would make that become 55. So I just set it equal to 55. I'm going to take away through 51 from both sides. So I get that 1/3 of x is the number 4. And now I'm just going to fraction bust, multiply both sides by 3, so that x is the number 12. So if I place 12 into this function, right, when I put 12 in for x, I'm going to get the number 55 as my answer. Right, and we are on to our last question. So first question of this last one says, hey, find a vertical line that goes through the point 87, and a vertical line. So I'm just going to remind myself that a vertical line is a line that's straight up and down. And I want a vertical line that's going to go through a particular point, a point where x is 8 and y is 7. So this is me sketching the point 8, 7. So there's 8, 7, and I want a vertical line, one that goes straight up and down. Well, as soon as I do that, I can see, you know what? Something is staying the same here, right? What's staying the same? Well, what's staying the same is every single point on this line, the x value stays exactly the same, right? Y's are changing. Y's can be really negative way down here. Y's can be positive way up here. But what's staying the same is the x value each time. We know that a vertical line has a slope that's undefined. And because the slope of a vertical line is undefined, we cannot write the equation of a vertical line in this format because this is an undefined value. So if part of an expression is undefined, the entire expression is undefined. So we can't write it in y equals format. But what we can say is, well, this is the line where all of your x's are equal to the number 8. That's a really clean way to do it. Something similar happens for a horizontal line, right? You would just say the y's are all equal to y's. But this is the equational line in which all the x values are 8. It's a vertical line. The next question says, find the equation of a line that goes through these points. And just as a quick reminder, I'm going to just write this to myself. I'm looking for the change in y divided by the change in x. I'm going to take my y value. I'm going to take this one that's listed second and subtract the first y value. And then I'm going to take that second x value and subtract the first. So that order, I have to be consistent there. That numerator is equal to -6 and the denominator is equal to 3. So when I reduce that, right, I get an answer of my slope is -2. So I know one of my two parameters, my slope parameter is -2. And I'll do this without point slope form first. I'll do this by finding the y-intercept. So I've got y is mx plus b. So if I want to find the y-intercept so I can write, I need to know both parameters to write this equation down. I'm going to pick one of my points, and just for convenience, I'll pick this point, right? And in that particular point that I've selected, the y value is 2. So I'm going to write down 2 for y. My slope that I found was -2. And I'm going to go and write down x, which is the number 1, plus b, that parameter that I need. All right, so this looks like the equation is going to be 2 is -2 plus b. And if I add 2 to both sides, I get my other parameter. I get my parameter b is the number 4. So I now have both parameters. I know my slope parameter and I know my y-intercept parameter. So I can write the equation of the line. It is y is equal to -2x and then plus the number 4. Okay. There's other ways I can write this, and either one of these would have been acceptable. Using point slope form, I could have written down y minus my known y value for that point I boxed in blue. So I can write y minus 2 is -2 times the quantity of x minus 1. And the other way I could have written it would be using, so this works for that blue box, but I could have also, I'll box the second point in orange. So I could have also written down the equation, I'll do an orange star here. I could have written down y minus my y value, which is -4. Well, y minus -4 is going to be y plus 4, and that equals -2 times the quantity of x minus 4. So any one of those three would be acceptable ways of writing the equation of the line that passes through those 2 points. All right, the last equation or last problem says, find the equation of a line that is perpendicular, right, to this line. Well, in order to do that, I need to know what the slope of this line is. I need to know its slope. And the format that it's written in, it's a little bit difficult to see the slope. So I'm going to clean it up a bit. I'm going to subtract 2 from both sides. I'm going to write 7y minus 4x is the number 10. Then I'm going to add 4x to both sides. So I get 7y is positive 4x plus 10. And I'm going to divide by 7. So y is 4 over 7 times x plus 10 over 7. All right, so what do I have here? The slope of this line that I was given is 4/7, but I need to find the slope that's perpendicular, right? So if it's going to be perpendicular to this slope, the slope I'm going to be using is -7 over the number 4. So this is the slope that I'm going to be using for my answer. It's opposite in sign and it's the reciprocal. And if I was to plot, 4/7 and -7/4 slopes on a graph, I would see, yeah, they're forming right angles to each other. The other thing that I have to do is use this one given point. So the point that I'm given is the point 12, 8. And I'm going to go ahead and use that point to find the y-intercept. So I know my slope parameter m, but I need to find the y-intercept. So I'm going to go ahead and let me grab this black pen, right? So I've got my x value and my y value, and I'm plugging things into y equals mx plus b. Y is the number 8. So I write 8 is -7 over 4 times my x value plus b. So I just have to find this b. 12 divided by 4 is 3. So this looks like 8 is -21 plus b. And if I add 21 to both sides, I get that 29 is what b is. So the equation of this line, right, you can see I've got the slope, I've got the y-intercept, should be y is equal to negative 7 over 4 times x plus the number 29. Now, in terms of like checking my answer, one of the things I always look at is, did I get the correct slope of the given line? So I might go through that again. And did I write the slope right? So I might check out that these are correct. And you can see I've got the slope negative 7/4 in my answer. The other quick check that I can do is if I feed the number 12 into this equation, it should be giving me back the number 8. So when 12 goes in, 8 has to come out because of this one given known point. So I believe this is the end. That's the equation line that has the properties required. The other option, of course, is that you could have written this answer in point slope form. So you could have also written y minus the known y value, 8, is the slope of negative 7/4 times the quantity of x minus the known x value, which was 12. All right, that's it for this Chapter 5 test walkthrough.